It's MR squared.
Exactly what kind of the exact same regular translational
This is
kinetics.
V squared. So this is half MV, half
No.
times plus half MV squared. Maybe it is, maybe when something gets even
Oh yeah.
all these answers, like I feel like one fifth
I think that's
one half
It's the same translational.
yeah, I is MR squared.
that is the
But this
Okay.
is
What do we say? Correct answer is C. Okay. Your free body extended. Well, no, we don't even worry about extended. We are just normal free body diagram are identical. You know, force of gravity, normal force, static friction. Force of gravity, normal force, kinetic friction. Now, I made this, I boiled this, cooked this up, so that the static friction is identical to kinetic friction. Super special case,
crazy.
okay? But it's valid, okay? The motion of the center of mass is determined solely by like a regular free body diagram, which is identical. The rotational aspect of that is just an added layer of complexity. You okay with that? Okay.
So extended free body diagrams, is that when you move the kinetic energy down?
The kinetic friction,
Yeah.
yes, and the static friction to the point of contact.
But normally you just keep it in
Normal you would put here. All right with that? Okay. Questions there? I'm going to run through, there's 4 questions in series. I'm going to I want, okay, so read the scenario.
Crazy is that compliment bigger than
It is.
okay.
No, Jay, that's not the size.
Less splash.
Okay. I was like, I feel like they're not normally the size of your head.
Now it just keeps the mess down. Okay, that's the first question. I don't want you to discuss it. Okay,
Wait, what?
that's the first question. Okay, these next 3 questions are exactly the same scenario. They're just more questions. Okay. Okay. For it. Anybody got a guess on this one? Question or answer?
I'm assuming that the string is the same length for both.
I mean, it's wrapped around these things. Is that what you mean, the whole length of the string is the same?
Yeah. Like is one wrapped around?
It's not, they won't become unwrapped fully. Like there'll always be some that is left on the spool.
Is one wrapped around 3 times, but 2 is wrapped around 3 as well?
No, it's just as many times as necessary.
So is the string unwinding as you?
The string is unwinding. Okay. Okay, different question, same scenario. Last question in the series, and then
These pucks are starting to rest, right?
mhm. Okay. Discuss. All 4.
Okay.
Definitely related.
Yes, that's right. Number 1, it's one. Because yeah, if you look at that, the greater the radius, the faster it will go. Like translation. Greater F times R is equal to I A over
Okay,
A
so
over
that
R.
makes sense, because if you're
So
thinking
bigger
about
radius, bigger acceleration.
to judge why it's because whichever one goes the further distance, you have more work done.
Well, it's the same. You have to spin it.
That's what I put.
Yeah, they're identical. So,
Which puck is greater rotation energy?
because think about the pulley, think about the pulley notice. It's not the same. No, because you're further from the center of mass. That only really matters when, like, if we're looking at how it spins, there's not the same radius around the same axis of rotation. Same axis of rotation. So the radius matters. So same inertia, it's where we're applying the radius.
The top right one is the only one I
It changes is the radius.
Because it has a greater pull.
So bigger radius, bigger
W omega, which is squared.
Yes, which is B over T, B over R, sorry. Multiply the R over. So let's go to number 2. I don't think I got number 2 right.
Correct answer is? Well, here, yeah, that's a good question. All right. Actually, let me give you a hint. I really hope you incorporated what you learned here. Go ahead and like keep talking.
So what
That was a hint. That was a really big hint.
That was a giant shove in our direction. So
Yes, but I don't know if you
the
can
center of mass,
just
the
put this in.
diagrams are identical. So that must mean
Yes, you can.
that
For
the
sure.
translation on this is just.
So, okay, we did that one.
Version is the same.
Yeah, we did most of it.
Okay, just like get behind that.
So
That makes sense.
Okay. Correct answer for this one is
C.
C. The same. Why?
Because the free body diagrams are done.
Their free body diagrams are identical. They're the same. They experience the same force. It's stated this right here. Therefore, they'll experience the same acceleration. I do not care where that force is acting on the object. The object's center of mass will behave in identical manners because they have the same mass and they experience the same force. Okay? As stated in the problem. Okay? So, this obviously is C. Because we just talked about it. Okay? Which one has a greater rotational kinetic energy? Correct answer is A. Because it experiences a greater torque from the force of tension. There's more work being done rotationally. More work. Okay. So work is force times distance. Work rotationally is torque times angular displacement. Okay with that? There's a greater torque from this guy because the radius is bigger. Okay? Which one has greater total kinetic energy? Which one has greater translational kinetic energy? Which one has a greater 1/2 mass times speed squared? Same. Which one has a greater total kinetic energy? Number 1. Where does that come from, though? That's what this question is begging. Like, how is that possible? Anybody have a stab at that?
Well, if the first puck has more work done on it.
Why does it have more work done on it?
Because it has a greater torque. Isn't that what we just went over?
It does have a greater torque, but there's also another thing.
greater distance,
Why does it have a greater distance?
the radius bigger,
Keep talking.
more force is being done over a bigger.
This is unraveling more. See, your hand looks like this in order to maintain the same force. You're doing more work to get that same force. Does that make sense? Which gives it more kinetic energy total. Same rotational kinetic, no. Same translational kinetic energy. But the top one has more rotational because it has more torque, but also it's spinning it's like from a force times distance point of view, you've got a bigger distance. From a rotational point of view, it has more, your angular displacement is great. How are we doing with that? There's some stuff that you can like capture on your notes. You just learn some stuff. Okay. make me convince you, like make me convince you that I'm right and you're maybe just confused.
You're wrong.
Like, if you're not satisfied, we need to have an argument. And that argument will probably benefit other people. Okay.
How do we know they have the same angular displacement?
Great question, they don't. This one has more angular displacement because it unravels more. It has a faster rotational speed, therefore it has greater angular displacement in that experiment. So more torque and greater angular displacement.
In that first part, why do we only care about the normal free body diagram and not the extended one?
Great question, because this one is asking for the speed of the center of mass. And that the speed of the center of mass is just, okay, some teachers teach free body diagrams as just a point. I usually teach it like you make a box with a belly button. Okay, that belly button is the center of mass. But some of them say, no, we're just condensing that object, whatever the shape of that is, to the center of mass. And the force is acting on that just, and so you would say, okay, some of the forces is equal to mass times acceleration, so your force of tension is equal to mass times acceleration. Independent of where it's acting on there. Okay, you learn, when you were learning free body diagrams, you did not take into account where that object, where the force was acting on the object. It wasn't until later that we added this layer of complexity of rotation that said, well, it does matter, but not for the motion of the center of mass. Like this is specific for the center of mass of the object. You okay with that?
So if you ever see like center of mass on the AP question, you should be thinking of free body diagram.
Yep.
or extended.
Correct. Okay, good with that? This is good, like we need to dig deep. Okay, make me convince you that like what I'm pitching to you is valid.
Isn't angular displacement like kind of arbitrary? Like, if one was to like do a full rotation, like its angular displacement is 0, right?
Oh, no, it's 2 pi, 360, whatever units you're using. It continues to go, so 2 rotations is 4 pi squared. Or 4 pi, yes, sorry, yeah. No, 4 pi, 6 pi,
So is there such a thing as angular distance, or is it just angular displacement?
only displacement. Yeah. Good with that? Good question. Okay. Woo!
Like these slides are designed to do that regular free body diagram.
Have a conversation.
Jules, if you look at the center center of mass, it's not moving.
I thought it's A or C because the strength itself is not.
So this is something called forces in the y
So the
direction.
center of
The
mass.
mass times gravity, like
It
where
says
the dude is holding it, that thing is.
Oh my gosh,
Mass times gravity.
reading comprehension is off the chart. Okay, mass gravity is greater than force potential because it's descending.
I was looking at the center. Center of mass going down.
You agree with me?
Mass force of gravity going down, but since it's going down. I like an elevator.
There's two tensions.
Because the thing going down, the same thing as
From point, I just don't foresee that happening.
Yeah.
I feel like it's gonna be one. Yeah, because you're holding it, it's technically one.
My thing makes sense.
As if unraveling to airport, it's rotating. We just know that the center of mass is going down. Which means mass gravity is constricting this potential. So even if the tension is applied twice, it's still gonna be less than mass gravity.
How much time did you guys spend on rotation?
Like a week.
Was it right before winter break?
We split it up between like before winter break and when we came back.
So it was like a week total.
Yeah, it's not spending.
Force of torque is going up.
We're a little lost.
Are your classes not normally this befuddled by
It's going
rotation?
this way. The thing is
So
unraveling.
Lovely.
Torque's going right
That's
here.
good for us.
So it has to go up to make this go down.
One Carl.
If it goes down, it
Just
would.
wait till you find out.
Oh my gosh, fluids. We
If
spent a
there's that
day,
fluid unit, it is not gonna go well for us.
like a day or two.
Okay,
What about thermodynamics?
correct answer is,
C.
good job. Okay, your extended free body diagram looks like this. Yeah, sorry, that was not very accurate. Okay, so some of the forces in the x direction don't exist, some of the forces in the y direction are not equal to zero. It's going down, so you're gonna make force of gravity positive. Okay, just like it would be if it was a descending mass. Okay, then you have the sum of the torques not equal to zero. If we make this the axis, the center of mass, the axis of rotation. Okay, we have force of tension times the radius because it's perpendicular. Is equal to I alpha. Okay, this is just like rolling but vertical. Okay, rolling down a ramp, but the ramp's really, really steep. Okay. So this becomes force of tension. It's a hoop, so mr squared, and then you're going to do A over R. Okay. You could, alternatively, say that this is the pivot point. Wouldn't necessarily recommend it, but it's doable. Don't do both. Pick one or the other. So some of the torques not equal to zero. Okay. So you'll have mg times the radius equals, what am I going to have for my I? You need to do parallel axis theorem. Because you're rotating not about the center of mass, but about the point outside of the center of mass. You're taking this to be your pivot point at that moment in time. Okay? And this is why tension does no work. And you can consider this as mechanical energy is conserved. Okay? So mgr is equal to mr squared plus mr squared times a over r. How we doing?
So if you drop the solid cylinder with the same weight, would it be like the same?
Nope.
No?
What would change? Okay, moment of inertia. What would happen? What would happen to this? What would change here? Same mass.
Decrease.
The setup would not change, but what numerically would change?
So tension would decrease.
Tension would decrease. Because a hoop has the greatest moment of inertia. A solid disk would descend faster or slower? Faster. It would have a greater acceleration. So you're taking, there'd be less tension to take away from the net force. The net force would be greater. How we doing? We digesting? Yee. Lots of brain matter being stretched.
Is it okay if we just look at the center of mass of the free body diagram? Because it's descending.
Yes.
Yes.
Yeah. To answer this question is just straight up this. I'm just like unpacking this scenario. This is a popular scenario. Just like rolling down a ramp is a popular scenario, this is a popular scenario. Okay? You can do a lot with this. I'm trying to show you all the stuff you can do. Okay? This is rolling down a hill that's just really steep. Okay? So, what would happen
It's slipping.
if it's slipping?
We got kinetic friction.
Okay? Does everybody understand the scenario? Like, okay? So, it's slipping and rolling. While it slips. Sorry, while it rolls, it's slipping. It's like, yes, no? Is that a possibility? Like, can you visualize it? Okay. What kind of friction would it be?
Kinetic.
Kinetic friction, because there's slipping and sliding going on between the surface and the ramp, or the ball on the ramp. Okay? So, is friction doing work?
Yes.
Yes. Is mechanical energy conserved?
No.
No. So all you do is this, mgh minus force of kinetic friction times the distance. This is your mechanical energy initial minus or plus the change in mechanical energy is equal to your final mechanical energy. This is how I like to set it up. You have freedom to do like the change in stuff, I'm fine. But this is equal to the work done by your non-conservative force, which changes mechanical energy. Big picture, we know that force affects energy, yes? Okay? We have baked up this measurement called work to help us quantify, put a number to how much force, how much a force affects the energy or changes the energy. So we say, oh, force times the distance that it's applied to, that's how much energy, mechanical energy is changed by. You okay with that? In a similar conversation, we've baked up this idea of impulse, this measurement of impulse. We're like, force changes momentum. How much does it change momentum by? Oh, force times the time that the force applied to it. That's how much it changes momentum. It's the same idea. One's just distance-based and one's time-based. Josh?
The friction times distance, is that encompassing like it rolling as well? Because friction's
No.
also related to roll.
That is not delta theta. That is this distance here.
Okay.
Is that what you're getting at?
Yeah, I see what you're
Okay, so it's the distance is like, okay? Oh, yeah. Yep.
Stab myself.
Oh, that's not good.
So, does the fact that it's rolling not provide to its velocity?
Does it not do what?
Like, when we say it's like going down with slipping.
Yep.
Do we assume, like, because it could still be rolling and like exerting.
Sure can.
So are we assuming it's just like ideal ice, or
Nope. There's friction. Okay, good question. If it was ideal, okay. Like problem solving, what you can do, a trick is to take it to the extreme value. That is a really popular technique. So if this was infinitely slippery, like no friction, what would this ball do? If this was a bowling ball, these finger holes would just stay without rotation. There's nothing exerting torque. You okay with that? Okay. So in order to get this spinning, it needs to do this.
Would the kinetic friction be the one that's applying the torque to make the ball spin?
It is. Okay, now, here's the catch. This falls apart. Okay? Because this relates the motion of the center of mass to the rotational speed. That no longer is valid. Okay with that? Okay. Yes, good.
That's always true if mechanical energy is not conserved.
What is that is always?
The does not equal.
No, that is if it is slipping.
So, if something is slipping, is mechanical energy always not conserved, or is there a scenario where it would be?
Man, always is such a dangerous word. I can't think of an example where it would be conserved if it was. I'm gonna say it would not be conserved because friction is doing work, which is a non-conservative force. Okay?
Yeah,
So,
that makes sense.
let's, so, we're gonna take this idea. Actually, can you stop this from crashing into the wall, please? Be my catcher. Okay? I'm going to think of a bowling lane. Okay? I'm gonna push this, just shove it like a knuckleball. Okay? This friction has a lot, or sorry, this floor has a lot of friction, so it's gonna start spinning real fast, but I'm gonna try to get it so you can see this. Okay? Go ahead and roll back to me. I'm gonna make it spin backwards, just so you can see the. Do you see that? Okay. One more time. Backwards. Okay. Alright. So, does everybody understand this scenario?
Yeah. Yes.
Both frictions are left.
Both.
Oh, okay, well, when it's going backwards, it's only kinetic friction, but once it starts to, well, there's no static friction.
Oh, okay.
Static friction.
Oh,
Oh, that's a lot of words.
Oh, your neighbor.
I think it's to the right. Technically, it's to the right. I think it's to the right. What?
I think it has to.
Oh.
Is that a constant velocity?
Wait, hang on.
Yeah.
Does not need to be friction. If it's already rolling, it's gonna keep rolling.
It's constant velocity.
There's no good. Oh, yeah, I can get behind it. There's no friction.
What's the friction?
If
It's already rolling.
And it's at constant velocity.
Yeah.
So if it, so it's already rolling. So if we just let it, say there's no friction. What?
I guess it doesn't. Okay, well there. Yeah.
So kinetic friction probably work on
Is there friction or no friction? We got to figure that out. So right there, normal force, gravity, that's in the y direction. If it's constant velocity in the center of mass, but friction doesn't work. So if velocity is constant and the acceleration is constant because the radius is not moving, so that must mean that the torque is constant of 0.
Correct answer is.
C.
Correct answer is C. Okay, look. Here's some arguments. If your free body diagram looked like this, how would the center of mass be moving? Accelerating. Okay. Okay. Block at rest. Block at rest. Free body diagram. Is there friction? No. Just normal force. And gravity. Okay. Yes? Same thing here. So at a molecular level, surface, ball, there's no sideways pushing on mountaintops and valleys. This is friction. Okay, here we go. There, at a molecular level, did I tell you this the other day? Yes. The force of gravity is a force, but then everything else is electric. Did I tell you that?
Yeah.
Okay, so this sideways stuff, we call that friction. That perpendicular stuff, we call that normal force. Okay? It just go. There's no pushing against the sides of the mountain. Okay? It just. Okay? So. Okay, so is everybody okay with no on this one?
Yeah.
Okay? We already talked about it. So is this.
No.
Same thing, falls apart. Okay? So. As this is sliding, friction, kinetic friction, looks like that, yes? Extended free body diagram looks like this. Okay, we're gonna make the way that it is moving the positive direction, we're gonna make the way that it's spinning, assuming I did a knuckleball at the beginning, and over time it's gonna be rotating clockwise. That's the positive direction. Tell your neighbor.
C.
Wait. Yeah, you would have to be losing acceleration in the center of mass.
Correct answer is
C.
C. Your center of mass is slowing down, but your rotational motion is speeding up until they catch up to each other. When the rotational speed of the rim matches the velocity of the center of mass, then it's rolling without slipping. Okay, so I'm going to run out of time. You can do a kinematic equation because the force is constant, and you can find the acceleration of the center of mass. Okay, and you're going to go until the final velocity matches the final rotational speed times the radius. This is where it ends up rolling without slipping. You can find a kinematic equation that with rotational acceleration, the time is the same. Your initial speed is whatever you started with. Your initial rotational speed is 0. And you have two different independent motions, but they're related to time, and they're related at the end, that's true. Woo! Pack it due tomorrow.